Hello everyone, welcome back to my series on Diophantus of Alexandria. This second episode is going to address the question of Diophantus' relationship to algebra as we understand it today. Scholars have actually argued fervently both for and against the idea that Diophantus was doing algebra in a meaningful sense. If one looks at Heath's book on Diophantus from way back in 1910, you can see that algebra is in the subtitle, and the front of this recent reprint really emphasizes that point by the choice of extract that's put on the cover. And the Greek edition here also advertises Diophantus' work as the algebra of the ancient Greeks. On the other hand, basic problems where you have to find the value of unknown quantities are already found much earlier than Diophantus, and on the other chronological side of things, the mathematical meaning of the word algebra and more importantly, a shift away from specific problems to writing up rules that will help you solve certain types of equation, that comes much later, especially with the work of Al-Khwarizmi in the 9th century. The disagreement about the nature of Diophantus' contribution to algebra continues today, and it basically stems from quite a philosophical question about which features of algebraic reasoning are the defining ones. And moreover, there's a lot of national prestige at stake in trying to identify the founder of such a major area of maths. So for this video, I want to sidestep a lot of those larger questions and much more simply just try and introduce some of the main points of similarity and difference between Diophantus techniques and modern algebra. Diophantus problems generally challenge you to find values for some unknown numbers which fulfill certain properties, and clearly this kind of problem is something we use algebra for. However, nowadays, we're normally looking for as many solutions as possible, whereas Diophantus generally sought a single solution, and as I said in the first video, one involving distinct, positive, rational numbers. Diophantus also, as in algebra, introduces a little bit of special notation to help him talk about these unknown quantities, and in one case, also various powers of that quantity. And I'll be discussing that further in just a moment. So there are clearly a couple of basic points of similarity. But important differences come into view if we consider an example, a piece of modern algebra like this expression on the slide. So one point is that this expression seamlessly combines powers up to 5 and the concept of a fifth root. Now, Diophantus does once or twice mention fifth powers, but he's much more interested in squares and cubes. And this reflects the geometrical way of thinking about numbers as lengths, products as areas or volumes that predominated in ancient Greece. That affected Diophantus' terminology and focus, even though in some ways it's actually remarkable that he doesn't express his solutions in more obviously geometrical terms. Another example of this slightly more geometrical attitude is that rather than talking about roots at all, Diophantus talks about the side of a square or a cube, the side of a cube being the cube root of the cube's volume. A second and particularly important point of difference is that the expression that we've used here has two unknown symbols, x and y, that we're using simultaneously. And of course, nowadays you can have as many symbols as you like in an algebraic expression. But Diophantus only used one unknown at a time. We don't know exactly what symbol he used for it. These mathematical jottings from a Greek in 2nd century Egypt, so not far removed from Diophantus' milieu, use a sort of S with a little line slanting down over it. In the much later manuscripts of Diophantus, the main symbols look a bit like this Y shape or a kind of curvy S. The symbol isn't a letter S as such, but that's how I'm going to translate it in these videos. And rather than the system of abbreviations that Diophantus used for all the different powers of S, the different species, as he calls them, I'm simply going to use modern power notation. I think that's much clearer, both objectively as a mathematical system and also in view of the people who are likely to watch this video and what they're used to. Now, the reason I said that only having one unknown symbol was really important is that it's a major constraint that actually shaped Diophantus' whole approach to problem solving. His aim is in fact to boil each problem down to a very, very simple polynomial in that one unknown symbol, either a linear equation or a quadratic with a positive rational solution in 99% of the cases. If you like, Diophantus maths is much more about creating very simple equations than it is about breaking down complicated ones. And so the main task is, how do you achieve that creation of a simple equation? And the basic strategy is to come up with very cunning substitutions that rewrite all the unspecified quantities in a problem, either as constants or as simple functions of a single unknown. Another consequence of only having the one unknown symbol to focus on at any one time is there's a great possibility for confusion, because sometimes Diophantus needs to change his focus in the middle of a proof, and therefore he changes the meaning of his one symbol halfway through. So, as an example of this, towards the end of his work, Diophantus starts using the following kind of transformation. Suppose we know that s is our unknown quantity, and we know that 6s squared plus 4s is some sort of square, the square of a rational number. Now, the unknown, the one that we were formerly calling s, can be written in the form 4 over s squared minus 6, where s is now some other unknown quantity. Right? So I've color-coded my s's here, but Diophantus couldn't do that. He just shows amazing confidence about his students not getting confused when he makes transformations like this. There are even a few times when he transforms s in this way within a single sentence. The third point of difference, going back to the modern expression we were looking at, is that it uses x and y as variables, so in the sense that any x and any y have this property. And Diophantus almost always uses his shorthand, his s symbol, not to express propositions about any number, but just as a placeholder referring to some specific unknown whose value he's trying to figure out. Of course, Diophantus did know that there were general truths that apply to all positive rationals. He just writes them out in words rather than using his symbol. For example, one problem in book 3 uses the identity on the slide there, and he expresses it with a full sentence. The product plus sum of any two consecutive squares makes a square. There are also a few times towards the end of his work when Diophantus uses his symbol more flexibly, as a parameter defining a whole family of solutions, what he calls a solution in indefinite form. For example, in book 4 of the Greek, problem 19 asks you to find, in indefinite form, 3 rationals such that each pairwise product is 1 less than a square. And after reaching the solution s plus 2, s, and 4s plus 4, Diophantus adds a sentence explaining that on this occasion you can plug in any positive value of s, and by adding that explanation, of course, he shows us that that wasn't the standard usage of his symbol. Well, of course, there are many other dissimilarities between Diophantus methods and modern algebra. For example, Diophantus didn't have a zero symbol, and he didn't factorize polynomials in order to reveal their roots. But for our purposes, I've just picked out a few points that I think really affect one's understanding of any of Diophantus' solutions. So, stepping back a moment, what is at stake in this discussion of how Diophantus compares to modern algebra? As I've said, for me, it's not really about who deserves to be called the inventor of important bits of algebra. The main point is rather to make an informed decision about how to approach Diophantus, given what you are aiming to do by reading him. Do you want to try and understand the strangeness of his maths compared to modern maths, or are you happy to translate his problems into more familiar modern terms? My aim in this series is very much about making Diophantus comprehensible for people who are studying or have studied a modern maths curriculum. So I'm going to use modern notation, and I'm also going to make some connections to graphs that Diophantus wouldn't have understood at all. However, one of the key points I do want to get across is how Diophantus had to think laterally to find all these cunning substitutions that simplify his problems, precisely because his toolkit was so limited, especially by this only having one unknown symbol at a time. Even for a mathematician with a modern algebraic toolkit, lateral thinking is a really key skill, and I think Diophantus can still help us practice it. So I am going to stick to Diophantus mindset in that respect, such as only using notation for a single unknown wherever I think there's no risk of confusion. So I hope it's become clear from this video why I wanted to tackle this topic before we dive into any particular problems. We will do that in the next video, starting with a focus on how Diophantus chose which feature of each problem he should assign his unknown symbol to. And I hope you'll join me for that. Thank you for watching.